แล้วผมตั้งคำถามว่าตัวเองแก่หรือยังแล้วผมก็เข้าใจว่าผมแก่เพราะบางทีผมก็ลืมนู่นลืมนี่นะฮะมีตอนเด็กๆไปอะไรนั้นไม่เข้าใจผู้ใหญ่เลยอะไรนะแว่นตาใส่อยู่กับตาแล้วถามแว่นแม่อยู่ไหนก็ใส่อยู่แต่แม่ถามทำไมหลังๆเริ่มเป็นเองนะฮะอะไรอ่ะกุญแจรถอยู่ในรถกุญแจบ้านอยู่ในบ้านเนี่ยกุญแจบ้านอยู่ในรถอืมอืมทำมาแล้วนะครับเรื่องเช่าประจำวันโอเคซาลีนะฮะไม่เป็นไรนะครับอ่า So we like to do forwarding, but again, sometimes we cannot do forwarding. A better idea is you reschedule. Put something up here. So when you put something up here, this one would move to the right, one cycle, right? And you use that wasted cycle for something else. So in a sense, a better solution for pipeline, not to stall. You use a combination of hardware and software solutions. You do rescheduling and you modify the hardware as much as possible. But at the end of the day, of course, we still have stall. It's normal. All right. And this is the idea of rescheduling. Like if you load and you know that, oh, the memory is so slow. By the time that you get R2, we have like maybe 3 instructions in between. So just move something down here and put it up here. That doesn't use the R2. That's where you don't have to waste 3 cycles for nothing. ครับเข้าใจคอนเซ็ปต์ใช่ไหมฮะเหมือนถ้าเทียบตัวอย่างไพป์ไลน์เหมือนอะไรนะตลกบริโภคเราเนี่ยหยิบช้อนส้อมหยิบนู่นหยิบนี่หยิบนั่นสมมุติว่ามันมีลวกก๋วยเตี๋ยวนานๆอยู่ซุ้มหนึ่งอยู่สต็อกหนึ่งนะครับถ้าเกิดว่าคุณเอาคนมาต่อท้ายแล้วมันโลกก๋วยเตี๋ยวไม่เสร็จสักทีมันก็ค้างอยู่ในไพป์ไลน์ถูกไหมฮะคุณก็เอาอย่างอื่นที่มันไม่เกี่ยวกับหม้อก๋วยเตี๋ยวมาเข้าแถวต่อแทนเขาก็สกิปสเตชันนั้นไปได้อย่างเงี้ยก็เป็นวิธีใช้ไพป์ไลน์ที่ฉลาดกว่า แทนที่จะต้องบอกรอก๋วยเตี๋ยวลวกแล้วระหว่างรอก๋วยเตี๋ยวข้างหน้า2-3ซุ้มมันก็ว่างนี่หว่าไม่ทำอย่างอื่นดิอันนี้เชิงเปรียบเทียบนะฮะจะได้เข้าใจง่ายๆนะครับ so that's the idea use something else do something else that do not have the data issues do not have data hazard like that reschedule okay and for the control hazard there is another idea so first idea is if we have a branch, we don't know whether we should go with next instruction or the one that we have to branch. ถูกไหมฮะ BEQ means if 1 and 2 is equal, jump to done, branch to done. But we would not know whether it's equal or not until the fourth cycle, right? But at the third cycle, we have to start something, or else we would waste the pipeline, right? So one thing to do is you can maybe guess. Let's assume that we might do the next instruction. So just put it in. By the time that branch is resolved, oh no, we don't need these 2 instructions. So just do not write the answer. But still, now we waste what 2 cycles for nothing. Right? อ่ะทันไหมฮะงงไหมฮะเหมือนผมบอกคุณเฮ้ยหยิบของในกระเป๋าออกมานะถ้าของที่คุณหยิบในกระเป๋าออกมาได้ลูกบอลสีแดงนะเดี๋ยวเรากระโดดมาทำตรงนี้ต่อแต่ถ้าหยิบออกมาแล้วมันไม่ใช่ลูกบอลสีแดงนะก็ทำคำสั่งถัดไปเพื่อนคนที่อยู่ต่อท้ายทำงานต่อ ปรากฏว่าคุณก็โอ้ยกว่าจะเปิดกระเป๋ากว่าจะรื้อของกว่าจะหยิบออกมาให้เพื่อนคนถัดไปมันเข้าระบบไปแล้ว2 คิวหยิบขึ้นมาอาจารย์ครับสีแดงปรากฏไอ้ 2 คิวนี้ผมก็บอกเดินไปเข้าไปคิวไปแล้วไม่เป็นไรก็ไม่ต้องจ่ายตังค์แล้วกันนะเดินออกไปเดี๋ยวเรากระโดดมาเริ่มตรงนี้แต่เท่ากับผมมี2 คิวนี้ที่ไม่ได้ทำอะไรให้เกิดประโยชน์ถูกไหมฮะอืมมันก็กลับไปลูปเดิม oh we hate stalling that's wasted cycle ถูกไหม that's wasted cycle so what should we do we don't like wasting yeah. So people propose then maybe we can do something better like one idea is let's try to delay the branch อันนี้พวกวิธีแก้ปัญหาฮะเดานู่นเดานี่เดานั่นว่าไปซึ่งจริงๆแล้ว Intel เคลมว่า branch prediction ตัวเดาว่า branch ไม่ branch ใน processor เนี่ยแม่นประมาณ90%แต่ในทางปฏิบัติเราก็บอก90%ก็ยังถือว่าห่วยแตกเพราะคุณมี instruction เป็นล้านๆ instruction เลย90%แปลว่ามี10%ที่คุณ waste cycle อย่างเงี้ยนะครับนะฮะ so we don't like stalling then we propose a design solution an architectural solution okay this is how it works let's say your original thought is like this we have add and then branch and all and you check whether this is equal or not and then you jump to branch Mhm. Okay the idea is we know that we would waste at least one instruction here waste one cycle here so let's redesign the branch instruction in a way that the instruction that right after the branch instruction has nothing to do with the branch delay the branch for one cycle and we ask the compiler or the software say move something here move something here in this case we move this one down that way we would do instruction number 2 do instruction number 1 and wait for the branch to result to go either number 3 or number 9 okay got my point redesign the schema of the branch instructions we call this delay branch let's delay the branch for one cycle and ask the compiler or the software we got one free cycle for you put something in all right งงไหมยิ้มแปลว่าอะไรบอกแล้วผมเป็นคนหนึ่งไม่ชอบสอนออนไลน์เพราะไม่เห็นหน้าคุณสอนในห้องเนี่ยเราอธิบายแล้วไม่เข้าใจนะสบตาแล้วยังรู้อ๋อคุณงงแล้วสอนออนไลน์เนี่ยไม่รู้เรื่องก็ใครไม่เข้าใจบ้างเงียบก็ the point delay the branch for one cycle do something else and we ask the compiler the software or the programmer hey I got one cycle here do something อ่ะคอนเซปต์จะประมาณนี้ let me use the same examples okay I ask you to pick up a ball from your bag หยิบลูกบอลในกระเป๋านะถ้าได้สีแดงนะกระโดดไปตรงนู้นถ้าไม่ใช่สีแดงนะคนถัดไปทำงานผมบอกผมขอเปลี่ยนใหม่ระหว่างที่คุณหยิบกระเป๋านะผมไม่รู้ว่าจะเป็นอะไรใช่ไหมคนอื่นเข้ามาทำงานเลย free cycle. Mhm. Changed by design to reduce the stall cycle. อะไร So if you know that your processor kind of support forwarding and delay branch, maybe you can do something with scheduling to avoid the stall cycle, or maybe you can get to the point that there is no stall cycle at all. เข้าใจภาพไหมฮะทันไหมฮะเหมือนฮาร์ดแวร์ข้างล่างมันมีปัญหาไงโอ้ย forward บางกรณีก็ทำไม่ได้ branch ก็มีไซเคิลที่ฉันต้องรอหยิบของอ่ะหยิบลูกบอลไม่รู้จะได้สีแดงสีขาวเนี่ยบอกเอางั้นก็ปรับดีไซน์เลยช่วงที่หยิบก็ไปทำอย่างอื่นดิกว่าจะรอเขาหยิบก็ไปทำอย่างอื่นดิเสียเวลา This is the graphic explanation of that. We delay the branch, so we have one free cycle. Do something else. Do something useful. By the time we sold the branch, now we got what we want. Okay? ผมพยายามช้าๆนะอยากให้คุณได้คอนเซ็ปต์นี่ถือว่าสอนแบบมินิมอลแล้วไม่ลงวงจรไม่ลงรายละเอียดอะไรข้างล่างเลยอธิบายคอนเซ็ปต์อีกเดียวเลย Right? We good? Okay. Maybe I move on. Okay. Let's try this exercise before we go deeper into the details of pipeline เดี๋ยวมีสไลด์ pipeline อีกชุดต้องเก็บนะฮะโอเคทำความเข้าใจคอนเซ็ปต์ก่อนครับ Okay. The question is why when we mixing store, branch, jump, and the R type, it doesn't create a structural hazard. เข้าใจคำถามไหม structural hazard เกิดจากอะไรนะแย่ง resource ถูกไหมฮะซึ่ง if you go back to my example in the previous slide here, we see that this is structural hazard because now we want to write to the register at the same time, meaning you use the load and add. This is 5 cycles, this is 4 cycles, and now we got structural hazard, right? The question is why then when we change from load to stall, suddenly there is no structural hazard. เข้าใจคำถามไหมทันไหมเมื่อกี้เราบอกว่าเรามีคำสั่งโหลดใช้5 cycle มีคำสั่ง add ขอโทษคำสั่งโหลดใช้4 cycle เดี๋ยวเอาใหม่ คำสั่ง load ใช้5 cycle คำสั่ง add ใช้4 cycle พอจับมาเขียนต่อกัน oh no we got structural hazard right now the question is why store branch jump which basically use 4 and 3 cycle when we mix with R type which use 5 cycles now we don't have structural hazard what's the difference why yeah the teacher try to explain the problem but there is no problem why to resolve yes this is the delay slot you do something else yes yeah all right the answer to this is actually quite simple this is 5 cycle right 5 cycle now we have 3 cycles but this 3 cycle basically ignore the last 2 so no structural hazard all right same thing now we have what 5 cycle no hazard
That's need to stir fry.
say that again
So that he just need to stir fry.
uh-huh
So it doesn't like it doesn't like come to the finish stirring.
right uh-huh it's like if you remember previous week I gave you an example like the first station you pick up spoon plate like that second station you get the rice right rice okay ดูให้มันเป็นข้าวแล้วนะนะครับ and the third station you do I don't know you pick up some kind of curry okay curry okay, whatever uh-huh and then you pick up drink and then you pay cash register payment something like that now for some reason what if somebody just pick up spoon pick up the plate pick up curry and leave that's fine right but if like first person would do this and second person say we would go for this and then this now you have conflict right one way to explain is put some number in and this is what 2 3 4 5 and 5 conflict okay but to understand it maybe you have to draw the pipeline diagram and put it in the details but I don't want to write the details you can do it yourself anyway just to understand yes please will the what yes of course if they ask you to draw something to write something they would have to tell you oh this is would use that many cycle this would use this cycle yes of course or if they may the question may say we will use the same notion like the one in the lecture that also another possibilities นะฮะไม่รู้ผมออกข้อสอบส่งไปแล้วผมก็ลืมไปแล้วงั้นผมก็จำไม่ได้ว่ามันออกอะไรไปบ้างวะนะฮะเริ่มเป็นคนหลงลืมนี่มันก็ดีเหมือนกันเนาะนิสิตมาถามข้อสอบออกอะไรครับไม่รู้ลืมlet's try this one we got 5 instructions this exercise quite simple can you draw the pipeline make a diagram that would explain the pipeline okay we can tryอือฮึถ้าผมคุณจะรอให้คุณลองวาดดูก่อนใช่ไหมก่อนผมเฉลยเขาใช้โจทย์ไว้ให้โจทย์อยากให้ทำอะไรมองออกใช่ไหมฮะโอเค maybe I try อือฮึ so we have what fish 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 เอ้ยขี้เกียจวาดรูปใหญ่ๆคุณไปวาดสวยๆของคุณเองแล้วกันนะอืม decode นะครับexecute ถ้าปกติมันจะวาดเป็นอีกสามเหลี่ยม ALU ใช่ไหมอืมนะครับ execute เป็น access นะครับ write back ผมขี้เกียจวาดเป็นไปวาดสวยๆของคุณเองครับโอเค now what load โอเค page decode นะฮะ execute อืมนะครับ mem access โอเค mem access read and then write back จุด alright what else ขอวาดสี่เหลี่ยมๆ5 อันพอขี้เกียจละหมายถึงผมเนี่ยไม่ชอบเขียนจอไม่ค่อยถนัดครับ okay do the shading yourself okay but let me explain the part that would be important to this so this one you would write back to R10 okay that's fine but this one you write to R12 that means you have to wait until this cycle so you can get R12 but next instruction say we need R12 right so one possible hazard here R12 right by the time you get R12 it's the end of the 5th cycle but we want to use it at the beginning of the 5th cycle so this is data hazard right okay let me use another color R10 and R10 now do we have hazard finish R10 here actually and this one say we need R10 here but we can do forwarding not a problem right So for R10, it's not an issue. Got it?มองไหมฮะ
Didn't John skip the SW or something?
Say that again.
Didn't John skip the SW while before?
อาจารย์เอาแถวที่3กับแถวที่4รวมกันครับ
Oh, okay. Sorry. Sorry. I should do this. Here we go. Should be like this. Not an issue, right? Because by the time that we want to use R10, we already write it back. Should be fine. Yeah. Okay, sure. Of course. Ah, เดี๋ยวขอตัดแปะเร็วๆแล้วกันนะเพื่อความสะดวก Copy อ่ะขอใจๆนะเขียนง่ายๆ add 1 2 3 4 5 okay let's add load 1 2 3 4 5 1 2 3 4 5 okay 1 2 3 4 5 and last one 1 2 3 4 5 like this. Okay. First instruction, we write back to R10. Okay. Second instruction, we write back to R12 and just use different color for R12. Third instruction, we say we need R12. So if we need R12, we need it here. R12 is needed here. Right? But we would have R12, the fastest is here. Right? It's like I ask you, pick up R12 from your backpack. And by the time you open the backpack and bring it up, well, it's the fifth cycle. Right? If you write it back, that's fine. But wait, I need it here. So we got one possibilities here. Data hazard. What else? It's not 12. Okay, some colors here. And do we have issue with R10? Well, we got R10 here, and we need it when? We need it here. Right? We need it here, but okay, that's fine. We got it already. So do nothing. Because I already write it back, right? I can read it. Good. All right. Same thing, we need R10 here, and it would need the thing at R10. Not an issue at all, because we already write back. So in this case, one data hazard from R12.
Why did you say the third behind R12 earliest after box?
The earliest that we can get is the box 4 because this one is mem access, right? And this one say, this is the address, put the result back into R12. So actually you got the data. even though you didn't put to R12 yet, but you got the data. So if you want to forward, you can just forward.
But the quick block is actually like.
The write back. So if for some reason we use R12 after this block, that's fine. No hazard. Yeah.
So I see friends after the people in the memory, right?
Right.
Why don't we just like use the article right after the votes, with the
Okay, your question is, why don't we use here? Because R12 is actually the result from the memory, so it's available here. This is the address 20 plus R5. You read it from the memory. So the real data is after you access the memory. Right? It's not the result from the ALU. The result from the ALU is the address, not the data.
So they have
Yes. Okay. Well, you can review that by yourself a little bit, but you now you understand what kind of expectation we want you to understand. You should be able to do something like this in the examination. Again, this is just the concept. Okay, I didn't go down into the circuit, the details. Just want the concept. We good? Can I move on to another topics now? Say that again. R10. Okay. Let's focus on the R10 for now. Okay. Okay. R10. You basically try to do R0 and R1, add them together and put it back to R10, right? So this is R0 and R1 adding. You got the result of R10 here, right? Did I answer your question? So we got the result here. That means if somebody want R10 after this point, I can just do forwarding. That's one possibility. But by the time we write R10 back, it's here. So we use R10 when we actually need it here.
After that, you can call back.
Yes. Right. We only forward if somebody want to use it before we write it back. But if I write it back to the paper, you want to use R10, just read from the paper. Since this is add, we have it before the memory, right? But this is load, we would have it after the memory. Load. Because load have to do memory access to get the data. Okay, better, good. All right, so I move on to the next slide. Okay. Now you got basic understanding of pipeline. let's spice it up a little bit, make it a little more difficult. Well, for data hazard, we got more kinds of data hazard. I show you an example of data hazard, but actually data hazard is much more complex than that. Okay, so we will see difficult kind of data hazard, complex kind of data hazard like that, and see how we can fix that. All right. Now, there are actually 3 more kinds of data hazard. Three more kinds of data hazard. We call them read after write, write after write, and write after read. You may notice that there is no read after read because reading doesn't cause a hazard. Only conflict between read and write or write and write that may cause the hazard. Let's try read after write. Simple, right? This is read. This is write. Read after write. So it's actually the example that I showed you earlier. Read after write. It's like you load something and now you want to use it here, right? You would not have the result here, but you want it here. That read after write. You pick up the data from your backpack. But wait, I need it now. You still pick up from the backpack. Okay, read after write. While you are picking up, I say, I want it now. And the second kind of hazard is like this. Write after write. Let me give you a specific example. Like again, now I want to load R1 with something, doesn't matter. But for some reason, right away, I say I add R1. For example. So what does it mean then? It means this one I write to R1. R1. This one I also write to R1. Okay, but by the time you're done with the load, it's too late. So I got the wrong data. Anybody that use R1 after this got the wrong data. You got my point? Okay, specific example. I ask you to pick up something from your backpack and put it on the first table. For some reason, you have trouble opening your backpack. It takes too long. And then right after that, I say, okay, now I put something else on table number 1. So anybody can use. You still busy with your backpack. I got new data already. By the time you're done, you put the data back. Now I got the wrong data. Got my point?
One is not properly reading our.
You got the wrong R1, right? So this is very bad example, but it explains the concept anyway. Right after right, I ask you to write to this, but by the time you're done, it's too late. Somebody else already write to that. Yes?
Or what what's the branch or app? It's like, like R1.
Uh-huh. So again, one way to do it, make sure that this one would finish later. Right? The second instruction would finish later, not before the one that come before it. This is right after right. And also this is another example. Right after read.
So this will be like we want to write before the word but second part function that.
Mhm. So maybe I show you an example like this. Let's say I want a equal sine x, for example. Okay. And suddenly I say x equal 5. Assuming that before that x may equal something else, maybe x equal 1. Okay. So I say I want to do a equal sine x, but you say, oh, the sine function takes take quite a long time to prepare the circuit. It's trigonometric function. I have to prepare the circuit until it's ready. It read the x, but wait, it got the wrong x already. Got my point? I ask you to do something. You say, wait, this is difficult operation. I need time to get ready. By the time you're ready, you pick up the data. Somebody already replaced the data. Somebody have already replaced the data. So you got the wrong data. So this is right after read. Well, of course, the classic one, the read after write, that's easy. I mean, easy to explain, but difficult to solve. The right after write and right after read, you can actually fix it by design. For the right after write, if you know that somebody will write to it, somebody before you will write to the same register. You just have to wait. We have special word for it. We call it in order commit. I cannot write until people before me write to that. So I have to write later in order commit. Yes.
I understand the analysis, but if we could diagram to it app, why is that?
Because in reality, memory can be pretty slow. Memory, slow. Like I asked you to pick up something from your backpack. Your backpack may be so big and you take time to look for things in your backpack. Slow. Large memory is slow. So when for load instruction, it can vary. It can be pretty fast or it can be taking pretty long time. It's slow.
Reloading to R1, but we're not using the R1.
Oh, again, this is bad example because in reality, we load to R1 and you may use R1 for something else before you replace it. Right? But by the time that you use it or replace it, it's too late. Like
R1 and one, in the load R1 and plan.
oh, it could be anything, just the address, right? It can be anything, doesn't matter. Okay, good. So this is the details of data hazard, which make it a little challenging to understand. This is lead error, right? I try to provide an example in high-level programming languages. Like in this case, I put C code for you. Lead error, right? I say A equals 7, but until A gets 7, I already use, I don't know, some random A's here. Right? Read error, right? And we know that forwarding is possible here. For the right after right, just do in order commission. In order commit. Like in this example, I say A equal something like that. Take some time to get A. Somehow you replace the A here and you get into trouble. Right? Because rather than you get A, which is 10, you get A from this data. So the in order commit basically say move this after the first one. So it can be avoided by design actually. But we will talk about this later because you have to learn another concept which is out of order execution, which we didn't learn about it yet. We can fix it anyway. Really straightforward. And the right after read, yeah, I gave you the same example earlier. Takes a long time to prepare. So again, we can just avoid by design by saying you take the X first, not here. Leave the X first. Right? Oh, by design mean okay, in a sense, rather than you say you read X here, I say you read X at the beginning of the cycle. So you got the original X, not the new one, right?
In X then go to the sign.
Uh-huh. Read X first, then do the sign later. Not prepare the sign circuit and then read X. Mhm.
So the sign is very good. Need to use it every when it's sign, not the layer.
Well, actually, we would do it in ALU, but sometimes you have to prepare something to make the ALU ready. Okay, and we already do this. I mean, we fixed the structural hazard by make it 5 cycles. We already do this, so this is just recap of how it works, just like that. Now that would get us to the point that how would we put the forwardings or the pipeline things into the processor? Let's start with how the data part works. Well, if you look at the data part, it's pretty straightforward. But the difference is now in each step of pipeline, you basically execute different instruction, right? For each step is actually different instruction. So I have to basically remember or pass the instruction for you to do in each step as well. On my point? Okay, let's compare it to the multiple cycle for the moment. For the multiple cycle, I say, hey, everybody, this is what I want you to do for the next 5 cycles. And everybody like share the same order from me for 5 cycles. But now with pipeline, I pick up the instruction, I pass it to the next one, so I also have to pass the instruction to the next step in the pipeline. Right? Then I pick up a new instruction. When I pass it to the next step, I also have to pass the new instruction as well. You got to your step, you would also see the instruction. Oh, this is what you want to do in my step. You pass the same thing to the next step. Oh, this is what I have to do for this step. So in a sense, you just pass the instruction with it. Unlike the multiple cycle, which basically say 5 cycle for now, you would do the same instruction. Now I say, I pass you something, instruction included. You finish it, you pass it to the next step, instruction also included. Okay. Or you can share the same decoder and just pass the control signal. That's another possibility. Yes. The previous one, this one, I say pass the instruction and let it decide what to do for that instruction. This one, I say, I already decode what to do. So rather than pass the instruction to you, I just say, in your step, this is what the control signal that you have to use.
Everyone asking to be the.
Yes. And well, it's still the state machine, but complex version of state machine. So don't worry about this, okay? But for the computer engineering, they have to do something like this for me. But for you, I'm okay. Just get the concept. Okay, let's try this. Maybe you understand how it works. Say I got about 7 instructions here. I try to explain how these 7 instruction works with the pipeline processor. Again, it may look a little confusing, but if you think through it, it's basic. It's pretty straightforward. Just lots of details, which make it look confusing. Okay, let's say this is our processor. This is our processor. So the first step, I say, let's fetch instruction 10. So basically, I put 10 to the memory, and I would get instruction. Right, number 10 here. 10 to the memory. So by the end of this instruction, what will happen is I would get instruction number 10 here, right? That would be instruction number 10. And you would change this to 14, right? And this would decode whatever happens. Basically, try to understand the load instruction. I'm talking about the next cycle, okay? Okay, next cycle. So the next cycle would look like this. We try to decode the first instruction, number 10. And now PC is now 14, right? Fetch the next instruction. Right? Okay, let's imagine what will happen in the next cycle. What would happen is that we would get what? We would get R2 here, and we would get what? 35 here, right? R2 and 35. All right, we should pass to ALU. That's what happened in the next cycle. And what do we get in the next cycle for the 14? The instruction number 14 would be here, right? And PC for the next one would be 20. Get the next instruction. Okay. So this is what happened in the next instruction. We got R2, we got 35, basically here. All right. And now we decode what? R2 and number 3. So R2 here. And we read 20. See how the pipeline works? Just keep moving things. Okay, imagine what happened in the next cycles before I flip the slide. Mhm. And use blue, then we would get what? R1 here, right? And we would get R2 and number 3 here in the next cycle, right? And this would be instruction number 20 in the next cycle, right? Okay, flip the slide. Here we go. The result from R2 plus 35 is right here, right? Feeding as an address to the memory. Okay. Blue. And in the green, we got R2 and number 3. This is R2 and number 3. Right? In yellow, you got R4 and R5. This is 4 and 5 for reading. Okay. It's just lots of detail, but it's pretty straightforward if you think about it.
This is the like instruction that you wanted.
Yes. Oops. Okay. All right. Imagine what would happen in the next cycle before we flip the slide. You would got the memory here ready for write back, right? Okay, maybe I change the color. Yes, and you would got R2 plus 3 here in the next cycle, right? And you would get what? R4 and R5 here in the next cycle. And this one would be the branch instruction. Right? Okay, let's flip it. Yeah. All right, pretty straightforward. Okay. Now Next cycle, what happened is that now R1 would equal, right? Because now we finished the first instruction, right? That's for the next cycle, right? Yes. And then this one would go here. Now, yeah, keep propagating. See, pipeline is not that rocket science. It's pretty straightforward, but you just have to apply yourself a little bit to understand how it works.
Think of a cycle, right? That's it.
Okay, so this is what happened. Right now, R1 finished. And the branch now decide 6 equal 7 or not. If yes, jump to 100. And if this is delay branch, that means the real branch would go here or here. Okay, so we got what? 30. Fetch already the all instruction. Okay, keep going. Now we have resolved the branch and we decide, oh, we have to go to the 100. Okay, so we fetch the 100. Keep going. Keep going. And actually, the part that would matter here now would come from this. Since we, for some reason, happen to face the add, and we know that we didn't really want to do add, so we just skip the right back. That's it. Got my point? We do the branch, even though it's a delay branch, but for some reason our design cannot resolve it. So it delay here. Yes. On what? Fetch 100. You mean this one? 100.
It's like why is there an X for this?
Why is there an X here? You mean this one? Okay. Because it say all R9 with 17. So when 17 is immediate, this is R9. So this doesn't matter. I don't care. X mean don't care. You don't care. It can be anything, right? Because what you use is, okay, maybe in red here and here. So I don't care. I didn't use X. Doesn't matter. In logic, X mean don't care. X mean don't care, and C mean not connect. X we call it dot care. Okay. For logic signal.
What's what's up? The black and the thanks for making see.
เอาใหม่ดิ R7 อะไรนะ
อันนี้แบบมันไม่ได้ทำอะไรแบบเขาตรงนั้นมันไปเข้าได้
Oh, okay. You asking about the branch, right? The branch basically say if this one is equal load 100 here. Uh-huh. Load 100 to PC.
But this also not not made.
Do not load it. Just plus one. Yeah, yes. Okay, we good? Yes, review it by yourself a little bit. Again, I told you it's not rocket science difficult, it's just too many details. Just like that. But if you apply yourself a little bit, just straightforward. Just lots of details.
Cái này làทำไมเป็นตัวคือแบบเป็นไอ้ตัวแรกที่เป็นแบบเป็นเอาคุณมาต่อแต่ก็คือแบบตัวสุดท้ายเอาคุณ
ยังไงนะไม่เข้าใจ
แต่ที่ดูแบบอันหนึ่งคือแบบตัวสุดท้ายตัวที่สี่
Ah, okay, I got your point. Well, this actually you have to go back to the instruction set architecture, right? This is the result, the target. But for comparison, this is overland. Right? This is a target. Yeah.
Like images so that we can later graph. But I was gonna apply the right jacket.
Oh, the 30, this is delay. Okay, and in this case, 34 is prediction. Yeah, it's just try to explain several concepts within one example. Mhm.
The right back and then.
No write back, no overflow mean we technically speaking didn't write the result of this instruction.
We are doing the one.
We going to 100. Oh, okay. This one is delay. Delay mean we're gonna do the 30 anyway. We're gonna do the instruction number 30, okay? But we still cannot resolve branch in time, so we just predict whether 34 gonna be executed or not. So let's assume that 34 would execute, then we fetch it in. But later we learn that, oh no, we actually want to go for 100. So we do 34, but we say we do not write the result back. So it's like we didn't use it. We only got one delay slot, right? But one delay slot still doesn't enough to resolve the branch. So we use one delay slot plus branch prediction. Yes. And plus 4 because one instruction is 32 bits, 4 bytes. So next instruction is 4 bytes away.
Oh, so I can see this delay so that, but by 24, if it doesn't break, it will be used correctly. Not as also the delay is there in the past slide.
Okay. Are we having fun yet? Well, I enjoy teaching this class, but I don't know whether you enjoy not or not. I like this subject, of course. That's why I do it for years and even write a book out of it. It's fun for me anyway, but may not be that fun for you, judging from your faces. Okay. I'm not sure if this is too detailed for you, but let me try to explain it, okay? Hazard detection. Again, if this is for computer engineering student, this is one things that they have to get through, because for computer engineering, chances that one day in the future they might design processor, they might work for Intel, AMD like that. Well, I don't know if your goal in life is not to go to Intel, and this is too detailed for you, right? But okay, let me try to explain this. We try to detect hazard, and we know that we got three kind of hazard, which is read after write, write after write, and write after read. Okay. Now to detect the hazard, like read after write, that means you got instruction I that come after instruction J. I after J, okay. I coming after J. So to detect whether we have a read after write or not, it means that for the write register that come before me, we got the same register that I try to read. That means we got a hazard, read after write. Okay. Well, this is the function, the map function that explain how we detect read after write, right? But in reality, it's like this. Oh, the instruction that come before me, they got write register, and I only read from RS and RT. So that means if my RS and RT intersect with the write before me, and it's not an empty set, we got read after write hazard. Confusing? Okay, try again. Let's say these shares, these 5 shares, they are pipeline. Okay. When I pass you something, I say, hey, this is what you have to do in the next steps. You got instruction with you for each share that I pass. Now I want to read something. I'm at the station number 2, the share number 2. I want to read something. I want to know whether I will get into trouble or read at the right hazard or not. So I look at the share that come before me and say, you have to write to anything to the 2 register that I want to read right now or not. Let's say I have to read number 5 and number 6. Anybody before me, do you have to write to number 5 or number 6? If yes, now I got read at the right, because I want to read number 5 and number 6, and guys before me, they have to write to number 5 or either number 5 or number 6 or both. Right? So I say, whoever come before me, if you have to write to something that I want to read, I have read at the right hazard. Explain in circuit. Okay? Just convert the concept to circuit, actually. But it's quite details, unless you have to design the circuit or design the processor yourself. But the concept is pretty straightforward, right? I just told you, I want to read from two registers, RS and RT, assuming it's number 5, number 6. Guy before me, if you have to write to number 5 or number 6, now we get read on the right. So the complexity is that in reality, you have to implement this into a circuit, convert it into a circuit, and put it into the processor. Okay. Now we can detect hazard. We can actually do the forward as well. Why? Because when we have to do the forwarding, it's just forward this back to here or forward this back to here. Right? So if you understand the circuit, the forwarding is pretty straightforward as well. We have one multiplexer that would forward here or forward here or forward here. And put it into A or B. Forwarding. Anyway, just a way to explain how the forwarding work in circuit. But if you find too difficult, okay, just leave it. I'm okay with that. But for computer engineering students, I would say implement this for me. Show me how it works in details. Or you want to work for Intel or AMD, that's the goal in your life, then we should do that. Okay, we good? Okay, few more slides and let's call it a day for today. And I reserve next week for review to get you ready for the midterm examination. So I try to finish this one today. Okay, and we know a case that the delayed load would not work, which is the memory access, right? The load from the memory. So there's one thing that we should do with delay load is we ask the compiler to put something in between, right? Like I have to use R2, but I know that R2 would not be available to forward here. So I have to put something in between here. So let's reschedule it, put something in between. Okay, we call that put something in between. We call it reschedule. For that, we don't have to stop the pipeline. This just shows some numbers here. Like if I ask the compiler to reschedule rather than stall the pipeline, this is the kind of performance that we get. You see in red, number of stall pipelines just smaller. Just some statistics. So that means compiler should be able to make good performance out of the software and processor. Actually, you also see this when you do the first exercise, the compiler optimization. They also try to do something like this. But whether you catch it or not, that's another thing. So modern architecture things, it's actually hardware, software for design. We ask compiler to do something, we put something in the hardware. And when working together, wow, it's fast. if we got good hardware, but the compiler did not adjust the software, it's slow. So specifically, actually, the compiler must also know about the hardware. Like, oh, I compiled this for what? AMD. Maybe I should do something. Oh, I compiled this for Intel. I should change something. So the way that you use your software like now, oh, I just download some binary and make a wish that it will fast. It's not always that fast. It may fast in some cases, but not always. Okay, and I think that's it for this slide, and we got few exercise to do before we call it a day. Okay, so pipeline pretty straightforward, but again, there are more kinds of data hazards, much more complex in details. And if you have to implement a circuit to make the pipeline work, challenging. The concept is simple. Okay. Let's try this. Okay. Simple. I got the diagram of my code here. Tell me what kind of hazard do we have?
Read after write. Hey, write after read, write after read.
Right after read, where?
Epsilon is aside anything is for the reduction and use epsilon.
Oh, so sorry. Let me use, okay, blue, epsilon, and epsilon. Okay. And what else? Possibility maybe R1 and R1 here.
Oh,
Or maybe R1 here. Just possibility. Okay. Okay. See that? Okay. And do we have hazard here?
One thing of read after write.
Okay. Lead up the right where?
Also converting function is one example when you R1, but in that way is already used the value to R1.
Got it? No. Okay. This guy is writing. This guy is reading. Potential for what? Write after read. But whether we have it or not, when do we write? When do we read? We write here. We read where? Here. Oh. So now we got right after read the blue. Okay. Yeah. How about the yellow? Yellow light. Right. We write to R1. We got it here. We read when? Here. And here. So it, yeah, lead after right. See it? Do we have right after right? Maybe? Yes. Right after right. Yeah, wait a minute. Too difficult? Again, quit is not an option, right? You should not withdraw this one, or else you have to meet me again next semester. I mean next year. So that's bad idea, I think. Try to understand the concept. Okay, I repeat, just understand the concept. That's good enough for you. That would make you pass this class.
So I have to write after the reads. So that I have to read after the write after this.
To read after write, yes. If you see something like this in the exam, you think you can do it? Maybe. Okay, good. And we got another one. Okay, let's try this one. Okay, this one, let me explain it a little bit. Let's say your hardware support forwarding and support delay branches, delay loads, okay? How would you reschedule the order, the code, to the point that there is no stall at all, if possible?
Correct.
So to do this, actually, you have to identify, oh, this is what? Read of the right, okay? And read of the right, and read of the right. And read of the right, okay. And also potential for this. Reschedule, move the code around. It has to be correct, but make sure that we would have fewest or no stop cycle at all. How to answer this? Let me do this. Well, you can do it with maybe with a diagram like this, right? Okay, F0 would be here. When do we need it? We need it here. Even though we have forward, that would be impossible, right? Is it too small? Okay, change the color.
Oh, in that.
Okay.
Also, that,
So that means we should move something up here. For my point?
first.
It look confusing, but again, if you understand the fundamental, it's straightforward.
What
Uh-huh.
is everything?
Same number, say.
Yes, just for this exercise, okay, but in real life, it's not the same number. It's much more difficult.
Would that be stated or will we, or is it just like?
If it's not the same, it will be stated in the equation.
So we want, if it was spelled as soon forget, five cycle.
Yes.
Then it's not stated before five cycle, but also otherwise it's.
To make it simple, just to ask the concept, I would try to use the 5 cycles, of course. But if I want to ask an advanced concept, okay, I will put something else. No need to remember. Nonsense. Okay. Okay, good. You can do it. Do I have to hint you anything else? Need more hint? Come on. All right, it's like this. You have to make sure that F0 and this F0 has at least one instruction in between, right? Again, F1 and F1, you have to make sure that you have at least one instruction in between. You may experiment a little bit, but the general idea is this. Let me, okay, I write then. Load F0. Okay, 0 R1. Okay. We need something in between. Let's move something down here. But since this one have to come before this one, so maybe I move the load up here. So I load F1 A R1. Here we go. Now I can just do the add. See, now one cycle in between. Okay, then I do the add here. Again, now one cycle in between. Right? Then we can do the store. F4. Well, this is what lead at the right. But since it's support forward, it's not that bad. But if we do it here, do we have hazard? No, because I circled them. Right? Doesn't matter. F5. Okay, here we go. Mhm. Right. And in fact, this one is a delay branch. So actually you can also move the sub down here. So I continue here, okay? Right? Because we got delay branch, that means things down here would get executed, always executed. So I move this one down here. Here we go.ไหวไหม Well, if you draw the diagram, it would hint you how to do it. If you can draw the diagram, like the one in this. It's just straightforward from the diagram. It's not outside loop because now we got delay branch. What is delay branch again? We have branch, the instruction that come after branch. Doesn't branch.
It's called, the branch have not been activated.
Uh-huh.
It's another dot.
So say that again. BNEZ, branch if not equal. Branch if not equal. Usually the branch instructions start with B in our class.
Branch did not execute it yet, but the sub command is only called.
Yes, yes. ไม่ต้องตกใจใจเย็นไม่ได้ยากอย่างที่คิดหรอกเชื่อผมดิตอนผมอายุเท่าคุณผมก็ทำได้ใช่ไหมตอนนั้นเทคโนโลยีมันแย่กว่านี้ตั้งเยอะวิธีสอนก็ห่วยแตกนั่งฟังอาจารย์พูดแล้วจินตนาการตามอะไรเงี้ยสไลด์ไม่ต้องอย่างนี้ Okay, good. Think so. Review it a little bit, but I think that's it for today. Any questions so far? Piece of cake, right? Okay, may I stop now? And let's call it a day. All right. Then we can all run for lunch.